Descartes' rule of signs. Descartes' rule of signs allows the calculation of the maximum number of positive roots and the maximum number of negative roots of a polynomial with real coefficients. The technique can also sometimes bound the number of complex pairs of solutions because each one of the solutions must be either positive, negative, or complex. The rule for positive coefficients is this. Count the number of sign changes in the polynomial. This number is the maximum number of positive roots of the equation. To find the total number of positive roots, reduce by an arbitrary even number. For example, the polynomial f of x equals x to the fourth minus x cubed minus 3x squared plus 5x minus 2 has three changes of sign. The first is from x to the fourth to minus x cubed, the second from minus 3x squared to 5x, and the third from 5x to minus 2. From the three changes in sign, the maximum number of positive roots is 3. All possible numbers of positive roots are then 3 and 1 because we can reduce 3 by an even number. It turns out that this particular polynomial has 3 positive roots. Now let's try the example of f of x equals x to the fourth minus 1. It has only one change in sign because we omit coefficients of 0. Thus, the maximum number of positive roots is 1. Therefore, there is actually one positive root. Let's try the example f of x equals x to the fourth plus x cubed plus x squared plus x plus 1. It has 0 changes in sign, so f of x has 0 positive roots. Now let's try something different. If we plug in minus x into a polynomial f of x, we can determine the number of negative roots, or less by an even number, by counting the number of times the sign switches in f of minus x. For example, try f of x equals x squared minus x plus 1. If we plug in minus x for x, we get f of minus x equals x squared plus x plus 1. Since the sign does not switch, we know that the polynomial f of x equals x squared minus x plus 1 does not have any negative roots. Now try f of x equals x to the sixth plus x to the fourth plus x squared plus 1. We see that f of x does not have any positive roots because f of x does not have any changes in sign, but we also have x of minus x is equal to x to the sixth plus x to the fourth plus x squared plus 1, and it doesn't have any changes in sign either. Thus, f of x has at most 0 positive roots and 0 negative roots. Therefore, since a polynomial of degree n has n roots, it must have 6 complex roots. Now let's look at f of x equals x to the fifth plus x cubed plus 1. It has 0 variations in sign, so it has 0 positive roots. If we look at f of minus x equals minus x to the fifth minus x cubed plus 1, it has 1 variation in sign, so it has 1 negative root. Thus, because the degree 5 polynomial has 5 total roots, it has 1 negative root and 4 complex roots. Now let's look at f of x equals x to the sixth minus x to the fourth plus x squared minus 1. The sign flips 3 times, so f of x has 3 or 1 positive roots. In f of minus x equals x to the sixth minus x to the fourth plus x squared minus 1, the sign also flips 3 times and therefore has 3 or 1 negative roots. Therefore, the remaining roots are complex, and because f of x has 6 roots total, it must have 4, 2, or 0 complex roots. Take the example f of x equals x to the fifth minus x to the fourth plus x cubed minus x squared plus x minus 1. It has 5 changes in sign, so it must have 5, 3, or 1 positive roots. Plugging in minus x for x, we get f of minus x equals minus x to the fifth minus x fourth minus x cubed minus x squared minus x minus 1, so f of x has 0 negative roots. Therefore, since the polynomial has 5 roots total, it has 0, 2, or 4 complex roots. If you like this video, be sure to like, comment, and subscribe. Tune in for more STEM content.